Welcome back. In this last segment, you're going to work on two examples of combinatorial proofs. First, let's start with this theorem. Let r and n be two non-negative integers such that n is greater than or equal to r. Then we have this equality. Remember that this n choose r notation is another notation for the number Cn, r, that is, the number of subsets of size r taken from a set of size n. Now this theorem says that this number is equal to the number of subsets of size r minus 1 taken from a set of size n minus 1 plus the number of subsets of size r taken from a set of size n minus 1. Now this identity is called Pascal's identity after the French mathematician and philosopher Blaise Pascal who lived in the 17th century. So, why don't you try and write a combinatorial proof of this theorem? Now, to get you started, let me give you a hint. So, for example, you can consider this number to represent the number of teams of R students that I can form out of a set of students, say the set of students in our class of size n. So that's the counting problem that you can use and whose answer is clearly this quantity. Now, why don't you try and find another way to solve this counting problem that gives you this expression? Please come back to the video once you have an answer and you're ready to check it against mine. Okay, so I want to determine how many teams of size R can I form out of a whole class of n students. So the first thing to notice is the overall set from which these subsets are formed have one less element than the total number of students in the class. So let's take a special student, say U. Now, do you agree that when I form a team of size R, there are two possibilities. Either you are on that team or you are not. Okay, so let's say that you are on the team of R students that I'm forming. Then how many ways do I have to form a team containing you? Well, the team is supposed to have a total of R students. Now that you're in there, I only have R minus 1 students to choose. And how many options do I have? Well, you're already accounted for, so there are only n minus 1 students left to choose from. So this number here is the total number of teams of size r minus 1 that I can choose out of a total number of students of n minus 1. And then if I add you to that team, then I have a team of size r. So that explains the first term in the addition here. Now, of course, the other possibility is that you are not going to be part of that team. And so what happens then? How many ways do I have to form a team that does not contain you? Well, then I still have to choose R students to form the team. But since you're excluded of the list of options, I get to choose them out of n minus 1 students. So in summary, this is the number of teams that contain you. This is the number of teams that do not contain you. These two sets of teams do not overlap. They cover all of the cases. So therefore, they must be equal. Their sum must be equal to the total number of teams of size R chosen out of n students. Now, let's turn to another theorem. It says, if n is a positive integer, then 2n choose 2 is equal to 2 times n choose 2 plus n squared. So I want you to go ahead and find a combinatorial proof of this theorem, which means I want you to find a counting problem whose solution, whose answer is one of these two expressions. So why don't you pause the video and figure out this first step in the proof. Okay, let me give you one possibility. Of course, you may have found another way to do it. Here is one possible counting problem. Let's say you consider the strings of length 2n. In other words, the strings of even length. In this case, n is equal to 4, so the string has length 2 times n, or 8. And let's say these are going to be bit strings, so the only possibility for each character is a 0 or 1. And I want to count the total number of bit strings of this length that contain exactly 2 ones. Every other position must be a 0. I claim that this counting problem has for solution this expression. Why? Because we have a total number of positions of 8, or 2 times n in general, and we must pick 2 of these positions to position the ones. And then, of course, the rest of the positions will be zeros. Now, why do we have 2n choose 2? Remember, in this notation, the order of the positions does not matter. Well, of course, it doesn't matter if you choose, say, this position and then that one to place the ones. There's no difference if you choose that position first and then that one. So the order of the positions doesn't matter. But you have to choose a set of 2 positions out of a set of 2 times n positions. Now, why don't you pause the video and try to find another way to solve this counting problem, whose answer is going to end up being this expression. Well, if we look at the right-hand side, we notice we have the expression here, n choose 2. So we must be choosing 2 positions out of n positions. So maybe an obvious first step is to divide this set of 2 times n positions into 2 equal parts of size n. And now we can split the total number of subsets of 2 positions into several cases. The first case is if the 2 positions we choose are on the left-hand side of that separation. In other words, in the first half of the string. So that's case 1. How many ways do we have to choose 2 positions out of a set of n positions? Well, the answer is n choose 2. That's case 1. Now, another set of cases that's completely disjoint is if the 2 positions we choose are on the rightmost half of the string. That's case number 2. How many ways do we have to choose 2 positions out of a set of n positions? The answer is the same as in case 1, that's n choose 2. Now, let's not forget there's a third possibility, which is we choose 2 positions, one of which is on the first half and the other one is in the second half. That's case 3. How many possibilities do we have? Well, we must first choose 1 position out of n positions. There's n ways to do that. And we also have n ways to pick 1 position out of the second half, or the n positions on the right-hand side. So we have n choices here. For each one of those, we have n choices there, so we apply the product rule. And so in case 3, we have n squared choices. Since all of these cases are disjoint and they cover all of the possibilities, then it must be the case that 2 times this number plus n squared is equal to the other way we had of solving the problem. And this concludes the proof, the combinatorial proof of this theorem. Now, if you started with a different counting problem, it's quite possible you were able to complete the proof in a completely different way. So that's great. Just make sure you also understand this other approach to this proof.